Okay, so in the last video we talked about FSMs, and on the screen here I've got an example of an FSM. But today we're going to be talking about languages, but these two topics are linked to each other, so they're going to be very helpful in relation to each other. So specifically we're going to be talking about DFAs, and just so we're clear, FSMs are a type of DFA. But let's start by reviewing what a DFA actually is. So this is the definition, textbook definition. I'm literally reading this off. It's a state-based machine used to recognize specific sets of strings. It consists of a finite set of states, a start state, a set of accepting final states, an input alphabet, and a transition function. So I guess watch the last video if you don't really know what's going on, but the set of states is pretty much like these things here, right? These things, and there's a finite amount of them, so they can't be infinite. The start state is shown by this arrow coming in from nowhere, pretty much. And accept states are these circles here, or states, which have a double circle around them. The input alphabet, which is used, well, the Greek letter sigma, which kind of makes it look complicated, but actually it's not really that complicated, means like what possible things can you input into the DFA. Well, in this case, you can even put in a 1 or a 0. So in this example, you would say that, the input alphabet would be 1, 0. Just written like that, right? Transition function. This doesn't really apply to this example, really. But transition function pretty much says, if you see this input, do this. Well, I guess for this example, the transition function would be, if you see a 1, you're just going to loop back to state 0. And if you have a 0, you're going to go to state 1. Now, the key thing about this video is to remember this fact. A language is regular only if it is the language of some DFA. Which is a bit complicated, but what it's really trying to say is a language is considered regular if you take the language and you can draw it as a DFA. So if you have a language, if you can draw it in this form, it's regular. So we can start with the first example, which is sigma asterisk, which is pretty much means all possible strings over some alphabet sigma, right? So over any defined alphabet sigma, what are the all possible strings, right? So suppose sigma, like the first example, sigma is equal to just 0, 1. Meaning we can input either 0 or 1. The question we need to ask ourselves, I guess, is can we design a DFA that accepts all strings made up of 0s and 1s, including the empty string? Well, the answer is yes, we can make a DFA with a single state that is both in the start and final state. So the state pretty much will loop on every symbol in sigma. So it has a transition for 0 and a transition for 1, and they both go back to itself. So it's pretty much like this example here. Not pretty much, it is this example here. We have an input of 0 or 1, and that will take us back to 0. Well, why does this work? Well, the DFA accepts every possible input, no matter what symbols are read. So it's going to always stay in this final state, meaning every string is going to be accepted. And if we just go back to the beginning and just remember the rule, a language is going to be regular if it's the language of some DFA. So for this language, can we represent it in a DFA form? Well, yes, we can represent it like this. So for that reason, this language has to be regular. Now, we can consider another example, which is the empty set, containing like no strings at all. We can kind of do the same thing as the first one. We can just build another DFA, and we can make a single state that is the start state, but not the final state. So there is no final states. And because there are no final states, there is no string that will ever be accepted. So that means that the language of this DFA must be the empty set, because there are no strings which can be accepted. It has to be empty. So for that reason, we have made a DFA which recognizes the empty set, and for that reason, it has to be regular. Once again, going back to the very important concept that empty set has a form by which it can be represented as a DFA, making it thus regular. Okay, the third example is the empty string using the Greek letter epsilon. Just don't worry about this one for now. We're going to come back to that. We're just going to be talking about this first one for the start. To prove that this is going to be regular, once again, we have to design a DFA which is going to represent the empty string. So the start state has to also be the final state, and any input is going to cause a transition to a state which is non-final. So this is pretty much what it would look like, and the reason why it would look like this is because this DFA is going to accept the empty string before reading any input because it's already in a final state. However, if the input contains even a single symbol, it moves to a non-final state, and it's pretty much, it's going to reject it. So this DFA contains exactly one string, this one, and it rejects all others. So if you put 1 or 0, any other alphabet into this other than the empty string, it's going to be rejected. So the language of the empty string is regular because a DFA exists that recognizes this precisely. This. It recognizes this on its own, nothing else. Only the empty string. So for that reason, once again, this is going to be regular. Now, I said let's not worry about this. Now let's worry about it. This is a bit different because we've modified it a bit and we've swapped which states are final and non-final. I don't know if you can tell, but we've just moved the 0 from there to there. So the start state is no longer final. The second state, which we transition to, is going to be final. So now the DFA is going to reject the empty string because the start state is not the final state, but it's going to accept a string that contains at least one symbol. So that is, it's going to accept everything except the empty string. So it's going to link this example and the empty string. So this is going to be expressed as sigma asterisk minus the empty string. So for that reason, this is regular because this is essentially expressed by this DFA. And this is saying that any string will be accepted except the empty string. And that's just kind of shown by the subtraction here. Yeah, my writing for the other one is a bit rough. This bit not neat, but that's pretty much what it would look like. We've got the empty string being subtracted from anything but the empty string to produce this DFA, therefore making it regular. So I guess the real takeaway from this is that every one of these examples can be represented in a finite way, that is with a DFA, so it makes them regular. And this kind of goes back to the idea at the beginning, where any regular language is regular if it can be expressed in a finite way, which is through the DFA. If you had, for example, some sort of language which was infinite, there is no way that could be regular, because by definition, a regular language is one that is finite.